Okay, on this video, we're going to use a power series to estimate the value of an integral. And so we're going to take this in parts. So the first step we're going to do is find a power series for the antiderivative of f of x equals e to the negative 5x minus 1, all divided by 3x. Now, the problem this comes from also says where f of 0, capital F means the antiderivative of this function. Remember, when you take the antiderivative, we usually put a plus c, a constant of integration. So this extra information there is going to be used to solve for c when we find that antiderivative. I know it's a little confusing when you see the problem, what to do with that. That's what they mean. Okay, so here's the idea. We know the series for e to the x. In sigma notation, it's just x to the n over n factorial, and you can expand out a few terms. So then you want to plug in negative 5x for all of your x's. In the expanded form, that's just like replacing each x with negative 5x, and in the sigma notation, you're literally just replacing x with negative 5x. Then we want e to the negative 5x minus 1. So this one's easier if you think of the expanded form. That's like taking this whole expansion, 1 minus 5x plus 25x squared minus 125x cubed over 3 factorial dot 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 minus 1. So you can see all that's going to happen is the ones are going to cancel. In the sigma notation, we can easily handle that by just, if all we're doing is basically getting rid of the first term, we'll just re-index our series to start at 1. And it's the same formula, just starting at 1. Okay, then we're going to divide by 3x, since that's what our f of x is. So each term would get divided by 3x. In sigma notation, we're just going to divide by 3x in the denominator. Now what we're going to do is simplify this. So we broke up negative 5x to the n as negative 5 to the n x to the n, so that on the next step, we could actually divide x to the n divided by x would be x to the n minus 1. And then in the expanded form, we'll just simplify. So each x gets knocked down a power. Okay, then the question asks for the antiderivative of this expression. So you can do it individually, term for term. Remember how it works for power series. X is our variable. All these other guys are constants. So when we integrate x to the n minus 1, we add 1 to the power, which is x to the n, and then divide by the power. So we have an extra n in the denominator. Plus c, plus a constant. So this antiderivative is what we're calling capital F of x equals that our series now, we've integrated it, plus c. If we use the given information, f of 0 is 0. If you plug in 0 for x, you're going to get 0 for every single term here. So f of 0 is just 0 plus c, which equals 0. So our constant of integration had to be 0, which means a power series, an infinite series that represents the antiderivative of this expression would just be this series here. Now, part B for this is now what we want to do is express a definite integral as the power series from 0 to 0.2. So say we wanted to evaluate that integral. And we know that the value of the antiderivative, the general antiderivative is we just found that, right, is right here. So think about the fundamental theorem of calculus. How we evaluate integrals is you would find the antiderivative and you would evaluate it from 0.2 to 0. So that's the equivalent of just plugging in 0.2 to our power series minus plugging in the lower limit of 0, which is going to give us 0. Okay, so this is just using the fundamental theorem of calculus. Now, to simplify this, it just so happens that if you combine negative 5 and 0.2, since they're both raised to the n power as one term, negative 5 times 0.2 just becomes negative 1 to the n. So this is our simplified infinite series that represents the exact value of that integral, right? It's an infinite infinite series. Now, of course, we can't evaluate all infinite terms of that series. So say we want to approximate that integral and make sure that our error is less than 10 to the negative third, which is 1 over 1,000. You can tell that this would have been an alternating series because of the negative 1 to the n. So by the alternating series remainder theorem, we know that the error would have been less than the next term, which would be by replacing all of your n's with n plus 1s. We're taking the absolute value, so we don't really care about the negative 1 to the n plus 1. And then we'll set our error less than 1 over 1,000. So we have this inequality to solve. And sometimes this happens. There's no algebraic way we're going to undo a factorial. So don't try to solve it algebraically. Instead, let's just do guess and check. And remember the thing with factorials is they get big fast. So it won't take a very big number before this fraction will be less than 1 over 1,000. And if you try n equals 4, you'll see that would be the first value that gives you a fraction that's less than 1 over 1,000. So what that tells us is we need to use 4 terms of our series to approximate the integral to within 1 over 1,000. And so then the last step is to just do that. If we just use the first 4 terms of the series we found in part B and just plugging it in, I'm not going to simplify the fractions, but this would be an approximation to that integral within 1 over 1,000. So it's a very accurate approximation. Okay.